Now for this discussion, we're going to pick one topic and we're going to write a 200-word summary explaining any important definitions, examples, and practical applications. Of course, you do not want to copy and paste just from any website. Alright, so the summary needs to be in your own words. A few resources are provided and we'll go through those real quick. And now for your second post, you want to choose one of your classmates that investigated a different topic. Review your classmate's summary and post a reflection on their summary and ask your classmate at least 3 questions to clarify your understanding of the topic. Lastly, you can pick another classmate and perform the same thing you did above, or respond to the classmate who responded to your initial posting. Respond to all the questions. Make sure, again, just that there is clear evidence of quantitative reasoning. Now you'll see in the instruction area, right when you first log into the discussion, you have your topics: mean, standard deviation, normal distribution, empirical rule, needs to be a T there, Pythagorean theorem, direct and inverse variation in functions. Now, in this video, I'm going to walk through just some examples and just the various things and try to explain each of these different topics to you. So as you scroll through the video, if there's one in particular that you wanted to look at more than the others, it's pretty simple. You can actually just click through and you'll see a title screen for each of the topics as this video goes along. So again, I'm here. If you need any assistance, please email or text message me. I hope you have a blessed day.
So I have this example here for you. It goes through and explains what standard deviation is, and I go step by step to show you how to create this chart. And so what I'll do here is I'll explain this example, but then I'm going to actually take a problem from the textbook, and I'm going to use that problem from the textbook and show you how to do that particular one in Excel. So here we go. Let's take a look here. So we have those test scores that we're working with. First thing you want to do is find the mean. So to find the mean, we added all these numbers up, and there were 10 of them, so we add them all up, divided by 10, and that's how we got this mean. Sample size. Well, there's 10 elements, so this 10 is a sample size. And so I try to actually use a chart, and I'm going to actually, like I said, we're going to do this in Excel as well, so you can see how the whole process works in there. So we'll list out the test scores. Those are the test scores. Now, to get the standard deviation, we have to take the difference from the mean. So what we did here is I took each of these element scores and I subtracted from the mean. So 22 minus 66, 99 minus 66, 102 minus 66, and so on. We subtracted it all from the mean. So, well, actually, if you think about it, test scores negative here don't quite make any sense, and sometimes that happens with standard deviation when you're trying to calculate it. So what we need to do to find the standard deviation is we end up squaring these numbers. And the reason why we square them again is so we're not dealing with these negatives that really, like that one, really don't make any sense. So once you square them, those negatives are gone. And so this is that process here. And this is you see sometimes the summation forms, and which is right here, the sum of the difference from the mean squared. Whew. So what that means, this fancy notation here that you see in all sorts of textbooks everywhere for this, is you take the actual grade or the value, subtract it from the mean, then you get all these values here. Negative 44, 33, 36. That's, again, taking the value and subtracting it from the mean. Then you square them. And so the difference from the mean squared, that's this column. And now the sum of the difference from the means squared is right here. So that's basically taking all those values and add them up. And so next what we do here is we take this sum and we divide it by n minus 1. So there's 10, so it's 10 minus 1 is 9. And this here represents the variance. And if you watch the intro video that I posted before, I emphasized that variance and standard deviation are extremely related. Over here, I have these values here, and I ended up squaring them. Well, I want to go back to the original form. This is the squared version here. So in order to really get something that makes a little more sense, I need to get back to the original form. So we end up square rooting it. And so when we square root that variance, we end up getting 30.4375 for this particular data set. And this ends up to be the standard deviation. All right. So I walked through this example that was already done, that I already did for you. Now I'm going to take you through a problem in the textbook, and I'm going to go step by step and how to do it in Excel. So let's take a look. So what we're going to do here is we're going to take this problem here. So we have this problem here, and we're going to go through step by step and just show different ways to calculate these various things. And I want to use Excel. I'm going to use a TI calculator just to give you guys just 2 more ways to utilize technology to your advantage. Now, in general, when you're doing discussion boards, when you're doing homeworks, now the MyStatLab, all the work is done there, so you're good. But for the discussions, if they ask you to show your work, you want to make sure that you can explain how you got there. And if you use technology, that's okay. Just make sure you explain and show that you understand how that technology actually gave you the answer. So I'm going to use 2 pieces here, 2 pieces of technology to help with some of the material for this first workshop. So right here we have this problem. 21 tractor trailer speeds are on a downhill stretch of I-90 where the posted speed limit was 65 miles per hour, we're recording miles per hour. So these are miles per hour of 21 semi-trucks. And so we're going to calculate the mean, the median, the mode, the mid-range. And then we're going to look at the range, interquartile range, variance, and standard deviation. So we'll look at all that stuff and see what exactly that means. And then I'm going to show you how to use Excel. Well, I'm going to actually do it at the same time, Excel and also the TI calculator, and how very, very quickly that those 2 items can actually get you your answers. So let's jump right into it. So let's take a look at Excel. Now in Excel, right here, I already have the numbers in there for us. So there's the numbers. The first thing I see here is calculate the mean. Well, what exactly does that mean? So mean, let's just go with that real quick. So mean. Mean is also the average. So that's the average. So that basically you're going to take all the numbers, you're going to add them up and divide them by the amount that you have. So instead of drawing all those out, we'll just do another quick example here. Say you have 4 tests. Okay, so you have 4 tests. You got an 80. You also got a 75. Then you started studying quite a bit. You got a 95 and a 98. So mean is basically the same thing as average. So you got 4 test scores, you add those puppies up. And so you got 4 of them, you divide by 4. And so that's how you get the average, or in this case, the mean. So let's do it real quick. 80 plus 75. All right, there's your total. And then we take that and divide by 4. And there is your average, there's your mean. That's your average, there's your mean. Average and mean are 2 interchangeable words. Median, though. Median, a little bit different. Median means the very middle number. The very middle number. So, median. So, let's take some numbers here. So, let's, and this is actually going to be extremely random. Just making this up right off the top of my head. So, we have numbers 2, 5, 7, 3, 1, 10, 12. So we have all these numbers here. We're going to throw another one in there. 3, and another 5. 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. All right, there's 9 numbers there. So the median, I want to find the median of these numbers. Well, the first thing I see is it's kind of all jumbled. To find the middle number, we probably want to put them all in order. So let's put them in order. So we have a 1, we have a 2, we have 2 3s. Any 4s? Nope. We have 2 5s. We have 7, and then 10, and then 12. Alright, let's make sure I didn't make any goofs here. 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. Okay. So let's try to find that middle number. So let's find the middle number. 1, 2, 3, 4. Alright, so that's 4 on that side. That's 4 on that side. So the middle number here is 5. So that's your median. Now, if there were 2 middle numbers, so say there were 10 numbers, you would take the 2 middle and average those out, and that would be your median. So the next thing, well, mode. What exactly is mode? Mode, all that is the number that occurs the most frequent. Now, up over here this data we have right above here, all these numbers, I'm going to list out the mode for that one. Now the 3 occurs twice, and the 5 occurs twice. Everything else occurs once. So this one actually has 2 modes. That is possible. It has 2 modes. Right? Mid-range. That's one that you don't see too often. Mid-range. Alright, mid-range. We're just going to use these same numbers here that we did for the median. Mid-range is actually going to be not exactly the same as median, but a similar idea. This one actually takes the largest number and the smallest number. So the largest number and the smallest number, and we average those out. And so that's going to be 13 over 2. And 13 divided by 2. Now I know some of you guys are like, oh, 13 divided by 2, I can't do that in my head. You have calculators, go for it. It has no problem at all. So 6.5. So that's 6.5. So that's looking at not the middle actual data number, but the middle value of the data set. So it's a little different than median. Median is actually the physical middle number. Mid-range is the middle value of the largest number averaged with the smallest number. So that's what those mean. And then let's take a look at this here. Range, interquartile range, variance, and standard deviation. Whew. Okay. We're going to jump into some technology here. So let's take a look at Excel here. All right, here's Excel. All these numbers here from this problem are right here. So let's figure out how to get the mean. Well, you type in the equation here, equals. Now, you type in mean, usually something will come out, but it didn't really come out. That's where you have to realize mean is the same thing as average. And there's our formula. You can click on it, or you can just type in there, parenthesis, and you can either type A1, or you can click and highlight, and hit enter. And there's our average for those numbers. And now, if you use Excel, you can manipulate this and make it look all nice and fancy. But basically, here, I'll put it over here. Mean. Actually, I probably should switch out, shouldn't I? There we go. Got the mean there. Now let's do median. Let's see if Excel knows how to do median. Yep, there it is. Median. And you can click and highlight. And there's the median value. Mode. Let's see if they got mode here. There is mode. Let's see here. Mode is actually 67. That's the one that curves the most. That's actually kind of unique because usually it's pretty rare where they actually end up to be the same. But if you do notice here, 67 does occur quite a bit. That's where it occurs the most out of all of them. All right, and mid-range. Ooh, let's see. It's not a typical one, but let's see if they have their mid-range. No, let's see. No, it's not displaying mid-range. So we can calculate that by just simply going like this, right? We can highlight this data, and we can do a data sort. So we can highlight the data. Let's do an insert. And I'm just basically going through, as if you're sitting there trying yourself. That's why I just started with the data and just showing you the different various things you can do in Excel. So we're going to list this here as miles per hour. All right, you can click and highlight. Now let's take the window down here so you can see what I'm doing a little better. I'm going to go to data, sort. Oh, hold on one second, sorry. Oh, I was actually doing it right the first time. Data, sort. It said expand the selection. I just had to hit continue. Sorry about that. All right, so we're going to sort. We sort by the miles per hour values and smallest to largest. So go ahead, and there we go. Smallest to largest. It ordered it for us. And so we're going to put our own little formula here. So we can go equals. And now you can actually physically put the numbers in if you want, or you can click on the cells. So that plus the largest one. Again, you can either put the cell or you can actually physically put the numbers in. And that's going to be divided by 2. And there's the mid-range. There's the mid-range. So that's 4 different numbers that you might deal with. The ones that you most likely will deal with more frequently would be mean for the rest of the course. These are all just descriptive numbers to help you visualize what the data kind of looks like. All right, so let's take a look at next. Range, interquartile range, variance, and standard deviation. Let's see what exactly those are. And let's see how Excel calculates those. Now, for range though, that's another one of those that is pretty simple, and there's not a set formula in Excel. But what the range is just simply the largest minus the smallest. So we can go largest minus the smallest. And that's going to be 21. So between the largest and smallest is 21 values, or 21 miles per hour. So think about it. You're on the highway, the fastest one's 81 miles per hour, the slowest one's 60. And we all know when you're traveling on the highway, that happens all too often. All right, interquartile range. Ooh, interquartile range. What in the world does that mean? Well, interquartile, all that means is the middle 50%. But how in the world am I going to get that? Well, first we identify the median. The median is 67. So let's highlight the middle number there. So we have 21 values here. So the middle number is going to be the 11th one right there. So let's highlight that guy. Just so you can see the middle. We have, let's see here, make sure I got the right one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, needed one more. Sorry about that. One more. All right, and then on the other side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that's the median there. That's the median. So how do we get the interquartile range? Well, we have to find the middle of this, or the first part, and the middle of the second part. So we have 10 values here. So let's see here. So we can do first quartile. So first quartile. Now all that means is that's just a big fancy way to say, hey, the first quarter of the data. So what we're going to do here is we're going to break the data up into quarters. You have the first quarter, second quarter, third quarter, fourth quarter. That's all that means. So the first quarter is just simply the marker that's telling you, hey, this is where the first quarter ends and the second quarter starts. So that's actually the median of the first half. That's all that means. So first quartile is the median of the first half. So let's do that. So equals, and then we're going to do median again, but this time we're actually only going to do the median of the first half, which is 64. So median of the first half is 64. And then we'll look at the third quartile. And the third quartile is just simply the median of the second half. So median of the second half. And so there's the median of the second half. Now, so interquartile range is just simply, so IQR, interquartile range, is the third quartile minus the first quartile. So interquartile, think about what that means. Inner. So interquartile, that's the two quartiles, or the middle 50%. And what's the range of the middle 50%? And so that's why we did the middle of the first half minus the middle of the second half. So we got the middle 50%. And so if you guys remember from middle school, we had these box and whisker pots. And here, actually, let's draw one. So if you guys might recall here. So back in middle school, you guys had these things called box and whiskers. So you had a whisker, and then you had a box, and then you had another little whisker, and let's see here. All right. So over here was the smallest value. This here, that value there was the first quartile. So this was the minimal. This was the first quartile. This was the third quartile. And this here is the max. So, and then inside here, now depending on how much data here, it doesn't always have to be right in the middle, but inside here, somewhere in there, will be the second quartile. Second quartile is just the median of the whole set. So it's the median of the whole set. So, again, another just graphical way to see your data. You get the minimum point, first quartile, second quartile, third quartile, the max. Interquartile range is just saying, hey, what's the median, or what's the, the range of the middle 50%? Range of the middle 50%. That's what that interquartile range means. That's all. Just a big fancy way to say, hey, what's the middle of the middle 50%? All right. Whew. Let's keep going here. All right, interquartile, now variance. Variance. So let's take a look at variance. Equals variance. Oh, I didn't have to type it all out. Now, see variance here. Now, this is something that we're going to start exploring. If you're going to use Excel, and also be careful with StatCrunch, there's two variances here. Variance of the population and variance of the sample. var.p, var.s. Now, typically, you're going to use the variance for the sample. And the reason why is this data is called a sample. Population would be as if you got the miles per hour for all the trucks that were on the road, which is near impossible. And so this is a sample, which is going to vary a little bit more than the typical, trying to actually get the full data set, because it's impossible with the full data set. It's kind of like when people do surveys. They take a sample. So, like for example, you get market research. They're trying to figure out what kind of shirts to put in the stores to get you to buy them. Well, they will sample their demographic and say the demographic's teens. It's impossible to sample all teens. Impossible. But they can sample a portion of them. And so that's the difference between those formulas. The sample one is going to do the variance of making as if it's a sample. Where variance with the population is that's basically telling Excel that you know all the data. So this here is just a sample, so that's what we're going to do. And so we highlight those, hit enter, and that's the variance. So that number there tells us how widespread our data is. And standard deviation does something similar to standard deviation. So standard equals standard deviation. Now this one here, again, same situation here. You got the P versus the S. So we're looking at the standard deviation for the sample of that data. And very often you'll hear something like, oh, this data, you're within one standard deviation of the mean. You're one standard deviation above the mean. And what that means is you're looking at the data and saying, okay, there's a certain percentage of the data that's within one standard deviation. A certain percentage. Now, if you're an intelligent person and you're told that your IQ is 3 standard deviations above the mean, well, that's pretty large. So what that says is you're like in like the 99th percentile. But that normal curve that I'm talking about, that I'm actually references, that's going to be next workshop. So this is what I mean by this stuff is going to be directly used in the next workshop. Standard deviation, variance. This stuff is going to bridge us right into what's called the normal curve. And it's going to help us to determine things like how many standard deviations is a particular value from the mean. And it's going to help us to come up with different probabilities. So that's just the 1 or 2 extra steps I was talking about before. But so this is just looking at all these different values using Excel to get them. Next, let's take a look at this here. This calculator here. This calculator is available to you to download. It doesn't work on Macs, I'm pretty sure. I've only seen them work on Windows products. But you might actually have a handheld too. So you might have a handheld calculator. And so let's take a look at how to use this calculator to calculate some of these values. Now, this one might be a little more limited on something like the mid-range and a couple of these other ones. So let's explore and see what it's capable of doing. Now, mid-range is one of those ones, I'll be honest, if it does pop up, it's pretty rare that it does show up. But so I just want to go over that with you because I know that word is out there. But let's take a look at what this puppy can do. So in this calculator, I know I have the values in there, but let's see how to use it. So let's go back to the main screen. So from the main screen here, after you click on, now one of the funny things about these calculators is, believe it or not, many students say they can't get it to work. They don't know why the buttons aren't working. If you get to turn it on, don't worry, you're not alone. It happens. But let's take a look here. So to get those values in here, we hit Stat. So this little Stat button here. And then we go to Edit. And that's where we input the values. So there's those values. So I inputted them already. Okay. So to try to find the mean, I'll go back to this main screen here. We can go to Stat. And then there's all sorts of stuff we have up here. We can go to Calc. And this here is actually going to be where you find a lot of your regressions. And then tests. Now this is going to actually be something that you're going to use later on in the course. The Z-test, T-test, all these sample tests. That's where that stuff's going to come into play. But for just regular descriptive statistics, we're going to actually hit second stat. So where it says list. Now in here, again, let me back up. Second stat. In here, we're going to go to math. This is where some of the more descriptive statistics are. Some of the simpler ones. And so let's take a look at what's in here. So I see mean, I see median, I see sum, I see product, I see standard deviation, variance. All right, so that's what I see for these. So let's take a look here, right? So we want to get the mean, so I click there, and then hit second stat, and we're going to pick L1 because that's where we put the data in. And there we go. And if you take a look, it might be rounding a little differently, but it's pretty close. Oh, actually, it is the same. It's just this one rounded here instead of there. So it's just this one just took it out a little further. All right, let's go to median. Oh, one more. Median. And second, what's that? There's the median. Same thing. Let's go. Let's see, get the rest of these. Mode here. Let's see here. So there is no specific way to find the mode. So let's see here. So we found, lost track, sorry. Find the mean, median, let's get the mode. There's no specific way to find it. But what we can do is, if we hit just regular stats, we're going to hit sort. And sort the list. And now if we go into the list here, so let's go into the list here, we can actually see that it's completely sorted for us. And so from here, we can just go through, 61 goes twice, 64 twice. And here we go. There's that 67, 4 times. And so since 67 was 4 times, it occurred the most, there's your mode. So there's ways you can use this to get each of them. And just like the mid-range. So mid-range, if you remember, the mid-range was the, take a look over here, it was the average of the highest and smallest. The average of the highest and smallest. And so, what we can do is, we can go like this, we can hit math, we can get the max, if you want, 81, and you know, you get the min, like this is if it wasn't already sorted, but you can get this information pretty quickly like that. And then there we go, now you know you can do 81 plus 60, and divided by 2. And there it is. The range, let's see here, range. Let's take a look at that one. Well, actually, you know, that one again, we just got the min and max. Range is going to be pretty easy. You just simply subtract those. And there's a range. And, alright, so let's keep going here. So, now this next part here, let's see here. First quartile, second, third quartile, interquartile range. Now, this is where there's a little trick in this calculator here. Let's go to stats. Now, there's no direct button that says this. It won't say first quartile, was it third? So, but this here is a great way to get a lot of this stuff all at once. So you can go to calc, one variable statistics. So if we hit enter on that, now from here you can choose L1 if you want to, but if you just had one var stats there, you can hit enter, and it'll actually list it all out for you. Or if you have more than one list, then you can do that and then the L1, and it actually lists everything out for you, all this stuff. And what you're going to learn pretty quickly is all this stuff, this x bar, the sum of the x's, sum of the x squares, standard deviation, so a lot of this stuff is actually listed for you. And so you can go individually and get each one, or you can do that one variable statistics, and you can get a lot of it. So let's take a look at what's here. And also, when I go through and make a video for the first, for the workshop discussions, I'm going to actually show you what each of these means. So let's take a look here. X bar, that's used in calculating standard deviation. So is the sum of the x's, sum of the x squares. That's all with the standard deviations. And if you look here, your standard deviation is there. And if you take a look, it's the same right there, 6.0134. There it is. And you're going to learn that this S means standard deviation of a sample. This little symbol here, you're going to learn what that is shortly. That's actually going to be the population standard deviation. So if that was just, so if that input that data, and that represented all the data, everything, then that's what the standard deviation would be for the whole population. But since we only have a sample, that's why this line here is more important. Now if you look at arrow here, we can start clicking down. It gives us the minimum. It gives us the quartile 1. It gives us the median. It gives us quartile 3. It gives us the max. And so the interquartile range would just simply be taking Q1 or Q3 subtracting Q1. So that also gives us all that information as well. Now, one thing that you do have to just take note of, standard deviation is very, very much related to variance. As we're going through and you're calculating, and if you're working on it by hand or whatever, there's a distinct, very, very clear relationship between the two. If you take this standard deviation here and you square it, you get the variance. if you take the variance and you square root it, you get the standard deviation. So they're very much related. You can't have, you can't, if you know one, you're going to know the other. So again, take the square root of variance, you get standard deviation. If you square that, you get the variance. And that's how they're related. So I don't want to drag this video on too much longer. I just wanted to give you a quick intro to some of the technology that you are allowed to use for this, this course. I just went through some of the different descriptive statistic type things: mean, median, mode, mid-range, range, first quartile, third quartile, interquartile range, variance, and standard deviation. And I'll make probably a more specific one about standard deviation for the discussion board. So just stay tuned to that, and I will be posting that shortly to help you guys get that started. So hopefully this was helpful. If you need any assistance, just make sure you just let me know. I'm here to help. I'm here for you, and I hope everyone has a blessed week.
The empirical rule is what our normal distribution is based on, or our typical normal distribution when in terms of plus or minus standard deviations. So the empirical rule is it's actually very simple. When we have our mean, the empirical rule simply states that plus or minus one standard deviation is going to hold approximately 68% of our data. Plus or minus two standard deviations is going to hold approximately 95% of our data. And lastly, plus or minus three standard deviations is going to hold about 99.7% of our data. So in other words, within plus or minus three standard deviations, what we're saying is the majority of our data is going to fall in between. And if it's outside of three standard deviations, it's most likely some type of outlier. It's out there. It's within 0.3% of a typical population of data. So again, the empirical rule just helps us and guides us into using our normal distribution, which we're going to go into in detail right now.
What exactly is this standard normal curve? So the area under this curve is always going to be 1. 1 represents 100%. 100% is because we're going to be dealing with probability. And so when you're dealing with these charts, all these numbers here, all these crazy numbers, now Excel can do it, the TI calculator can do it, and I'll be using those when I post a video about to help you a little further with the discussion for this week. So, but just in general, let's just get to know this curve. And what exactly is a z-score? Whoa, what is a z-score? So let's go over what exactly is a z-score first. And then that can help us to figure out what the probability is at that z-score. So let's take a look at z-score first. Okay, so let's take a look at those the formulas to standardize a z-score. So this one up here, the top one, please don't mind my penmanship, sorry about this, I'm not the greatest of writers. This standardized z-score on the top is representative of more population figures. So the mu here, which is this weird fancy looking u, is very similar to the x-bar. The u represents the population mean, the x-bar represents the sample mean. And so say you have some data, it's most likely a sample, it's very rarely a population, and so that's why sometimes when you hear about sample sizes, and the larger the sample size, the more reliable, more representative it is of the population. But we'll get into that later. So now this one here is sigma, and that's S. And then the S is just simply the standard deviation of a sample. Sigma is standard deviation of the entire population. Now there are some times when we can get entire populations and data on everybody. Like the census that goes around every, I think it's 10 years. But there is times where that actually can occur, where you get the entire population and data from everybody. So this is going to be what we use to standardize the scores. So let's go back and take a look at this first example. We'll do a couple of these here. Mean of 10, standard deviation of 2. So mean of 10, so x bar of 10, and we have standard deviation of 2. And so we don't have to go back and forth. We're going to do a couple of those examples here. So number 1 was an x value of 10. All right, let's get a couple more here. Let's do a couple of these. Okay, we'll do 26 and 18. Or, yeah, we'll do those. We'll do the 14, I should say. So we'll do 14. We'll do 18%. And we'll do 6. So we'll do 4 of those, just to see what to do. And then we'll try to figure out what exactly this means and bring it to a standard normal curve. All right, so let's quickly do this. Here we go. So we're just going to plug those into that formula and simplify. All right, so we have and now again, if you have a couple of these values, you can always work backwards to get to whatever variable that you're trying to find. So say you had the x value, x bar, and standard deviation. Okay, sure, you can get the z value. But say you're given the z value, and you've got to work backwards to find another variable. You can definitely do that. So depending on the question and the situation, and you can now always solve for one of the variables. You've got to make sure you have the other information. But in this case, we have the x bar, we have the s, we have the x value. So let's go ahead and let's work on this. Okay, so here we go. So we have 10 minus 10 over 2. Oh, this one's an easy one. 10 minus 10 is 0, so that's going to end up being 0. So that standardized z-score is 0. Oh, I should probably put a z here so nobody gets confused. Over here, so this z-score, 14 minus 10 over 2. And so that's going to be 4 divided by 2, which is going to be 2. And over here, I'm just going a little quickly here, don't mind me, 18 minus 10. So that's going to be 8 over 2. 8 divided by 2 is 4. And we'll do one more here, one more. So z equals, we have 6 minus 10 over 2 is going to be, now this one you got to be careful of. This one here is going to be, alright, so this one's going to be actually negative 4 over 2. Now, I didn't simplify it in one step like I did the other ones. Just emphasizing the negative simplifies to negative 2. So what does all this mean on a standard normal curve? Well, standard normal curve. What does that look like? Well, that's one of those bell-shaped looking curves. So let's draw one out here. And now, this might not be the best, but I'm going to try. It's not too bad, not too bad. I've done it a lot worse. So let's take a look here. So in the middle here, in the middle, we will typically have our x bar or mu, one of the two. So we'll just start out with mu. That's where the average is right in the middle, so 0, or in this situation, x bar is 10. So in our situation here, x bar is 10. And for just the population in general, going towards the standard curve, this spot here also is where sigma is 1. So that's where sigma is 1. In our situation, that's where S is, where the standard deviation is 2. Sorry, I'll stop it there. So where in the world do the rest of the values fall on this chart here? Well, let's take a look. First one, well, the first one's easy. X bar, x, and the mean are the same. So that first one is right at the mean. X equals 14, that's 2 standard deviations above the mean. So that's actually going to be over here. Now, I'm just obviously estimating here. So that's going to be 14 over here. Or we should say standard deviation of 2. So that's going to be S value. Not S value, sorry. It's basically standard deviation of 2. So 2 standard deviations. Now, next one, 18, that's 4 standard deviation. That's going to be way out over here. So that's going to be 18 over 4. 19 over 4, but 18, but 4 standard deviations above the mean. And negative 2 would be down over here. So that's below the mean. So you might hear, sometimes you hear expressions of, you're below the means, 2 standard deviations below the mean, 1 standard deviation below the mean, or above it. like the 14, 18. So 6 is two standard deviations below the mean, which is also -2 in terms of the standard normal curve. But what in the world do these values actually mean? So we're going to focus on those z-values now. We're going to focus on those z-values. So we're going to another example, and let's take a look here. We're going to look at these probabilities. Yeah, so we'll look at these probabilities. So we have some probabilities we're going to find. And we'll go ahead and we'll look at these first three. Now these first three, as I'm looking at them, they're all going to be related. And you'll see what I mean when we go through and work this out, as I'm just glancing at the calculations here. So let's get a brand new fresh page. Let's take a look. Let's draw a standard normal curve here. Hopefully we'll get one good or better than the last one. I'm not always the best at making those bell curves. Alright, so we're given here x equals 9. So x equals 9. And mean of 3, standard deviation 3. So, whoops, mean of 3. So x bar 3. And standard deviation of 3. Alright, so let's get the standardized z-score. So standardized z-score, so that's going to be 9 minus 3 divided by 3. So that's going to be 6 over 3, which is 2. Alright, so this here is going to be over here. So that has a standardized z-score, so z equals 2. So standardized z-score of c equals 2. Now over here on this other page, oops, let me go back here. Make sure I was labeling it correctly over here. Alright, so over here, these values here were the z-scores. Let me sure I labeled those correctly. And these ones here, when I put those here, those were the x values. Those are the x values. And we were translating them into the z-scores. And so that's what we did with this example. And so, let's see here. So we're trying to find the probability. Just make sure we get them correct. X is greater than or equal to 9. And so what that does is that translates into z is greater than or equal to 2. So what in the world does that mean? Well, this is where we're going to go into that standard normal curve. Let's check that out. Alright, so what this does here is these charts, and now again the TI-83 calculator that I have on the screen prior, and Excel also does this for you as well. But I'm just showing you kind of where they're drawing the numbers from. So we have this here, and where it's shaded, so based up to the z value, this table gives you the probability. For example, if you came up with a standard score of 1. So a standard score of 1 means 1 standard deviation above the mean. So we're about actually where that z value is looking right there as we see it. So let's zoom in a little bit to see better. There we go. So this is just an example. That doesn't mean that the z is right where the 1 is. This, I'm just saying, for just as an example. What that means is 0.8413. That means 84.13% of the shade of the area is below that z value. So that's what that means. So what we're looking for here for this problem is the probability of x is greater than or equal to 9, or standardized z-score, z is greater than or equal to 2. So let's go to 2. Here's 2, 0.9772, 0.9772. So 0.9772. The thing is, that represents the area that's over here, up to the z-score. But we actually want the z-score for greater than. So we want what's here. So the bell curve, the standard normal curve, the area under the curve is always going to be 1. So if we know this larger part, we just can simply take 1 minus that, and that'll give us this part in here. So let's do that real quick here. So 1 minus 0.9772. There it is, 0.0288. Oh, I'm sorry, oops. 0.0228. Okay, keep that number in mind as we're doing the next two problems. So that's the probability over here. Now, next we're going to do x equals 6 and then standard deviation of 3, or mean of 3, standard deviation of 1.5. And we're looking for less than this time, less than. So same concept that we're doing, except it's set up a little different, not much different, a little different. Standard normal curve. That's where the middle would be, the mean. All right, so this time we have an x value of 6. We have an x bar of 3. We have a sample standard deviation of 1.5. All right, so standardized z-score. Z equals 6 minus 3 over 1.5. So we end up with 3 over 1.5, which is 2 again. So that equals 2 again. Huh. It's kind of odd. It can happen. And like I said before, these are all with the way these numbers are worked out, they're all actually purposely that way, so you can see the different ways the probabilities come up. All right, but we have to think about this one because we're actually looking for the probability this time of, well, so let's just go right to the z. The z is less than or equal to 2. So this time we're looking at that standard z-score over here of 2, and we're looking for the area below it, because we're looking for less than. And we already know that answer. We're not even looking at the chart because we already did it right there. So this one here is going to equal 0.9772. And then we'll do one more where we're looking at in between. All right, so in between. Oh, actually looking at this one, it's actually pretty simple. Mean of 0, standard deviation of 1. You see something like that, this is already in standardized form for us. Already in standardized form for us. So let's take a look. Let's go and see if we look back at the notes. Yep, right over here. Trying to find where we did that. Oh, right there. Mean of 0, standard deviation of 1. So that's the standard normal curve. So a little messy here, but that's where we did it right there. So whenever you have mean of 0, standard deviation of 1, that actually already represents, so this one here already represents the standard normal curve, so there's no need to standardize it. It's already standardized. So this time we're looking at between -2 and 2. So we're looking at between -2 and 2. So let's draw this real quick here. Okay, so what we're doing here is we're actually trying to find the values between here. So between these two. All right, so we know the area all the way up to 2. We already know that one. We did that twice already, 9772. So we know the whole area, but we have a little piece that we want to try to get rid of. We wanted to get rid of this part. And so we can take the area of the whole piece up to the 2, and then subtract that, and we're good. So let's do that. But first, we have to get that value. So let's go over here to -2. Oh, there it is, and right there. That should look familiar to you. 0.0228. 0.0228. So I'm going to take that and subtract 0.0228. And that's going to equal, well, let's do it real quick. So we have 0.9772 subtract 0.0228, and we get 0.9544. 0.9544. And so that's going to represent the area all in the middle. Now, just another note here, that was 0.0228. Well, before we also found that that was 0.0228. Now, the standard normal curve is symmetric. I know the mess that I just drew isn't exactly symmetric, so please don't mind my I'm not an artist, to say the least. But the standard normal curve is indeed symmetric. So if you go through that chart that we had up there, so we go through this chart, so let's take a look here. So like, for example, if we looked at -3, 0.0013, you go all the way down to regular 3, 0.9987. Yeah, it doesn't look the same, but if we do this, ready? 1 minus 0.9987, and there it is. So the area above that is the same. So it's very symmetrical. So this is a very symmetrical type curve. Standard normal curve is symmetrical. All right.
So this here is going to be your content review, your ALEKS review for this last workshop. And let's just jump right into some questions. So the first thing on tap is the Pythagorean theorem. A squared plus b squared equals c squared. And it's probably something that you've seen time and time again. So let's take a look at where it comes from. Well, let's think about a square. So say we have a square. And, well, the area of a square, if you think about it, area of a square is going to be this side. Now remember, all sides are the same for a square. X times x. So that's going to be actually x squared. So each of these here represent a square. But isn't it that this deals with a triangle? It's kind of weird. So let's see what we mean how the squares and triangles relate. So let's get a more visual. So remember, a squared plus b squared equals c squared. These are all taking a single side and we're squaring them. And we're saying there's a relationship here. Well, where does that relationship come from? So let's take a look at this. And this is a program that you do have available to you. It's free for download. It's called, let's see here, I'm not sure how it's pronounced. It's basically geometry and algebra kind of smushed together. GeoGebra. Don't ask me for pronunciation. I'm not very good with the pronunciations. Anyways, so we have a triangle here, a right triangle, because the Pythagorean theorem holds true for right triangles. So where do the squares come into play? Well, here they are. So if we look here, this side here is a size of 3. Now remember, for squares, all the sides are the same. So let's go 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. All right, so we have a square. All right, so now we have a square here. Whoops. And so now let's look at this one. This one here is a side of 4. So let's do 4. 1, 2, 3, 4. Right? Or did I, let's see here. 1, 2, 3. Oh, it's a 3. Let's back that up a little bit. All right, sorry. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay. And so now, if we get one more square in here, so let's get a square. So this one here, we can actually count the diagonals. So let's do that real quick here. So before we do that, let's count those diagonals. 1 diagonal, 2 diagonal, 3 diagonal. All right, so let's count those and get another square. 1 diagonal, 2 diagonal, 3 diagonal. 1 diagonal, 2 diagonal, 3 diagonal. 1 diagonal, 2 diagonal, 3 diagonal. All right, so I was just going there and counting, just simply counting where those, just to make sure that we got squares. That's all I was doing there. Just make sure we got squares. So this is where the Pythagorean theorem comes from. Let's scroll and make this a little bigger so we can see it. So we have this triangle here, this right triangle here in the middle. Attached to each of those sides is a square. So this one right here has a side of 3. This one has again 3. And now this one here is, well, we don't know that one, but we can figure it out. That's actually how the Pythagorean theorem can be applied. Because it's diagonal. Yeah, sure, it's 1, 2, 3 diagonals, but that's not the actual length because we have to actually figure that out. And so we can figure out that side with the relationship of the Pythagorean theorem. So this one here is 1, 2, 3, and that's 1, 2, 3. So we have these two areas of these squares. And now this is how it all applies. The area of this square and the area of this square will actually equal the area of this larger square. So if you combine the areas of those two squares, we will get the area of this larger square. That's how this actually applies. So let's see the actual math behind it. So let's put this to the side. Let's get that in the screen there. Okay. All right, now we got it side by side. Here we go. So in this, so we have these two squares, and we have this larger square. And let's actually go ahead and do it. So let's go to another page here. So we have, this one here is a 3 by 3, so that's 3 squared, plus, well, this one here is another 3 squared, but we don't know that other one. That's c squared. Not sure about that one. So 3 times 3 is 9, plus 3 times 3 is 9, and that's going to equal c squared. 9 plus 9 is 18. And so we have c squared. Now to get rid of a square, we do take the square root, so we take the square root of both sides. And so we have the square root of 18 is going to equal that other side. Now, you don't have to do this in the course, but this can be reduced. There's a perfect square in there, which is 9. So this does reduce to 9 times 2, square root of 9 is 3. Now, you don't have to do this as part of this course, but I'm just showing an application here. Okay. Now, that one has a little bit messier numbers. I'm going to do one now, another example with some nice numbers where it's no radicals. So let's go through that. Here's just a very similar example. I just adjusted a little bit. I took this square here and I made this side of this triangle 4. And so each of these sides of this square now are 4. This one is still 3. But how did I know where to put these points for this particular one? They didn't really line up exactly like diagonals or anything like that. Well, this is how. Here we go. This triangle, just like the one before, there's actually 4 of them. And they're all around this square. If you take a look, this diagonal here is, now this is a square, it should be the same as this diagonal, and this diagonal. They all should be the same. So let's check. This one, we have 3 and 4. Well, let's take a look. As this turns, we have 1, 2, 3, 1, 2, 3, 4. So if you take a look here and you try to rotate this square, you end up with the same exact picture except the triangle's now on top. If you rotate this square again over here, so we rotate it 90 more degrees, we have 1, 2, 3, 1, 2, 3, 4. And then rotate that 90 degrees again, 1, 2, 3, 1, 2, 3, 4. And so this triangle, this Pythagorean theorem, or actually a Pythagorean triple, you're going to see this one turns out to very nice numbers. As we rotate this square here, this triangle is on the outside of it 1, 2, 3, 4 times. Because that diagonal represents the 4 sides of the square. So this square here is a 4 by 4. This square here is a 3 by 3. So let's get this other side and figure out what this square will be. So here we go. Let's do this. So again, we have a squared plus b squared equals c squared. So it's going to be 3 squared plus 4 squared equals c squared. So that's going to be 9 plus 16. And 9 and 16 gives us 25. And now, this one's, as many of you guys are going to see it, this one's much simpler. Square root of both sides, square root of 25, square root of c squared. It's going to be 5. Now, some of you are going to be like, wait a minute, if you take the square root of both sides, it's actually plus or minus. But since we're dealing with geometric distances, there's no negative distances. So that's why we're ignoring the positive negative. It's just a 5. So this here is a Pythagorean triple, 3 by 4 by 5. So all the sides here are size 5. All of them represent the sides of the square. 5 times 5 is 25, so the area of this square is 25. And think about it, 9 and 16, areas of those two squares, add up to be the area of that square. And so this relationship holds true. And so any triangle that satisfies a squared plus b squared equals c squared will always hold this to be true. The squares that are extended out from the two smallest sides, the areas of those two, will equal the area of this larger square. So that's where the Pythagorean theorem came from. So that's where it came from. So let's keep going on and do some examples. So for this example, we have a right triangle. And now we have to make sure we memorize across the right angle. This little square here represents a right angle. That's going to be the longest side of a right triangle. That's going to always be C. That's the key one to remember. This one over here, remember, addition is commutative. So if this could be A or that one, either one, doesn't actually matter. So let's set this one up here. So we end up with x squared plus 9 squared equals 15 squared. Okay, so x squared, and now 9 squared is 81. 15 squared is 225. Oh, that was a bad 225. Sorry about that. And subtract, so we have x squared. Now if you're not sure what that is, let's just pop it in here real quick. Minus 81. And we're left with 144. 144. And now we take the square root of both sides, we end up with x equals 12. X equals 12. There we go. So that side will measure 12. So that side here is going to be 12 for this to hold true. Again, it's a right triangle. And for a right triangle, the Pythagorean theorem will hold true. Now, it will hold true, a squared plus b squared equals c squared. Now, this says nearest hundredth. Now, sometimes you will get a decimal as an answer. But an unrounded decimal, it'll still hold true. That's like before when I had the example of 3 radical 2. But, you know, just for this case, we're going to be rounding if that's the situation. We're going to round. We're not going to get into the radicals right now. All right, let's go to the next example. So this here is just a word problem. I mean, it has a picture for you. It's all set up for you. You just make sure you use the Pythagorean theorem correctly and just answer the question appropriately. So this one says find the length of the ladder. So the ladder is leaning against the house here. If you notice, that's the side that's across the right angle. So this time we're trying to actually find C. So we're trying to find C this time. So let's take a look what that looks like. Okay, so 7 squared is 49. 24 squared, oh, sometimes I transpose the numbers, so let me do this one real quick. All right, 576. You know, I'm not perfect. I'll tell you, sometimes I have most of these memorized, but for some reason, my mind wants to transpose the 7 and 6. That's why I did it real quick. Okay, equals c squared. All right, so let's add those together. Plus the 49 is 625, and then so that's going to be 625 equals the c squared. Take the square root of each side, so square root. We end up with 25. So 25. So that means this, the length of that ladder is 25 feet. 25 feet. All right, let's keep going. So this one here, this is the distance between 2 points. Now there is a distance formula. In my opinion, that distance formula is messy. I don't like it because there's a lot of square roots, a lot of this. I recommend you drawing it. So let's go ahead and draw it. I'm going to use that same calculator I just had up before, just to draw it to show you that there is a triangle there that we can use, and we can use the Pythagorean theorem, which will make this look much easier than what the distance formula shows us. So let's take a look. So here it is, the same graph. So we have negative 9, 9, negative 2, positive 1. So let's use the Pythagorean theorem. So inside this, we have a right triangle. It's right here. Ready? There's one side, and there's the other. And there's our right triangle. A squared plus b squared equals c squared. So this squared plus this squared will equal that squared. Let's count. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay, so let's use the Pythagorean theorem. So we have 8 squared plus 7 squared equals that length of that side. So we have 64 plus 49 equals to c squared. All right, let's grab that calculator. So we got 64 plus 49. All right, that's see, that right there is going to end up being an irrational number when we take the square root. So this one is going to be one where we're going to have to round. So let's take the square root of that, and we get this messy number right there. So we end up with 10.63. Now again, if you go ahead and get this is a free download. This is free. There's apps for the, I believe the Apple, the Android. I don't have a smartphone, but there's apps for all sorts of things for this particular one. If you notice, it actually gives you the estimate of the segment here. So it actually helps to verify it and check yourselves. All right, so 10.63. And let's make sure here, give an exact, oh, it says give an exact answer, not a decimal. Okay, so let's go back. So an exact answer, this is decimal, exact answer would be the square root of 113. So this here would be more of an exact answer. Why? Because it does say exact. So we want to make sure we distinguish that. Okay. All right, so let's keep going. Direct and inverse variation. Direct and inverse variation. Now, relating it back to something that we already know, y equals mx plus b. This side here, this is actually directly related, direct variation. It's when the b value is 0. So it's where the intercept is at 0. So this actually goes through the origin. So y equals mx. The b doesn't necessarily have to be there because it's 0. So when something is directly related, it follows this relationship right here. Now when something's inverse related, take a look here. This is m times x. Over here it's m divided by x. It actually, the x is actually inverted into a fraction. Inverse, so when something's not directly related, inversely related, we're dealing with the inverse. So just like I wrote here, most texts use k rather than m because there are many application problems where m is frequently used as a variable. So in the textbook, instead of seeing the m there, you normally would see y equals, and they use k here, times x. So when it's directly related, this k represents the constant of variation. Now remember, constant of variation, that is the slope. Remember, slope is how things consistently change, what's the rate of change. So that's how this k represents the m. It's the same thing. Now, for the inverse, like I said, it uses k here because it just wants to distinguish between many other formulas that you might see and variables. Again, the x is inversely related. It's inverted. Basically, what I mean by inverted, this is the same thing as having k times 1 over x. Inversely related. That's what that means. So let's take a look at some examples here. All right, first one here. Trey's earnings vary directly. It actually said it very explicitly here, directly, with the number of hours she works. Suppose that he works 6 hours yesterday and earned 96. If he earned 128 today, how many hours did he work today? So we can figure out the constant of variation, which would be k, in essence the slope for direct variation. So let's see, it varies directly. We have 96, it works 6 hours, so 96 divided by 6, 16. So we know that that is going to be y equals 16x. And we know that because it said varies directly. And now think about it, it's a typical application problem here. You work 0 hours, you get paid 0. All right, so now it says he earned 128. Well, that's the result, that's the output, so that's going to be y. So 128 equals 16x. And so we just simply divide here. So 128 divided by 16 is 8. So he worked 8 hours. So that's directly related. Now let's look at an inverse relationship here. So we'll go to inverse. All right, so it says the time it takes to cover the distance between two cities varies inversely with the speed of the car. The trip takes 12 hours for a car moving 46 miles per hour. How long does a trip take for a car moving 24 miles per hour? All right, so let's figure out what that K is. All right, so 12 hours, 46 miles per hour. So 12 is the result. So that's going to be the Y. So we have 12 equals K over the X. And so that's going to be 46. All right, and so now what we have to do is multiply. So we have 12 times 46 is 552. So that's actually what K is going to equal. So K is going to be equal to 552. And so the equation we're going to work with is Y equals 552 over the X. All right, let's see what we have here. So how long does a trip take for a car moving 24 miles per hour? Okay, so this time we're given the input. So it's going to be Y equals 552 divided by the 24. All right, let's do that real quick. And so it's divided by 24. And so it's going to be 23. So it's going to be 23 hours. All right, so again, direct versus inverse related. Direct related, it's like a line that goes through the origin. Very simple. Inverse related, the X is inverted. It's now dividing by X instead of multiplying. This question here, let's take a look. We have inverse varies inversely. So I just generally scan through for keywords. So varies inversely. So we're going to look at that relationship where the X is inverted. Let's take a look at what affects one another. So we have 14-inch long string. It has the 450 cycles per second. So we're dealing with these vibrations. Now the length affects the cycles, which means the length is independent and the cycles are dependent on that. So looking at this as the X, this as the Y. So the 12 will be the X, and then we're trying to find its Y. So let's take a look at how to set that up. And there's a few ways to think about this, but let's take a look at how to set it up. So we can do it the same way we did it before. So we had the 14 inches, and that produced a 450. And we can go ahead and find the K in this fashion. So we can go ahead and find the K in that fashion. So we'd be multiplying both sides by the 14. And so it would be 14 times 450. And so we have 6,300. So 6,300. Okay, so we have the K value. Now we can plug it back in. And so we end up with Y equals 6,300K is the K, over X. And now we want to know about the value of the 12. And so the value of the 12, that's going to go in place of the X. So 6,300 divided by 12. And we end up with about 525. So about 525. So that's one way to set it up. Here's another way to set it up. If we actually take the K and we isolate it. So up over here, if we do X times Y. So if we take a look at this here, let's focus in on the formula. And so if we take the X and multiply on both sides, we end up with X times Y equals the K. Now, the constant variation is exactly what it says, constant. And we know the constant here is the 6,300. But if it varies inversely, that means that every X times Y is going to result in that K value. So what that means is, if I do 12 times 525, that has to equal the 450 times 14. So the given information we had was this. So we could have done 14 times the 450 like we did. And that must equal, according to varies inversely, must equal the 12 times its y value. And so we could have actually solved it using this relationship, which just comes from the formula. It comes from that form. And that's actually what we did. We did the 450 times 14, and then we actually divided by 12. Here, we would multiply. And then on this side, we have multiplication. To get rid of that, we divide. So either way ends up with the same thing. Either way. So just another example for that function notation right from Alex now. This is the functions f and g are defined as follows. It just says find f of 6. So all that means is we're going to put 6 in place of x in that equation. Or excuse me, that function. And then g of -3, we're just going to put -3 over there. So let's see what that looks like. So f of 6, we plug that right in. Now do not mistake this function notation for multiplication. That's not multiplication. This is just plug in. It's just showing us how we're plugging something in. And we're just simplifying this other side. So -3 times 6, -18. And then we're taking 3 more away. And so it's getting more negative, so -21. Over here, -3 to the third power. Oh, let's make sure we don't forget this here. So 3 negative. Now, again, just get in the habit of doing parentheses just in case, depending on which calculator you're using, to the third power. Oops, third power. And then times 3. So we're at -81. But this time we're adding 5. So we add 5 here, and we result in -76. So again, functions, function notation, just another way to express something. It's just actually showing us, physically showing us what we're inputting in. This is the input. The result over here after you simplify is the output. Input, output. That's what that is. Just another way to display a relationship.
And so we're actually going to write some of these equations in function notation. Because what you're going to see is they're very much related. It's just a matter of how things are displayed. So this first one here, typically, function notation, the most typical one is f of x. Now, a lot of times students will look at that and they will say, whoa, so I'm taking some variable f and multiplied it by x? That's not necessarily the case here. What this is just symbolizing something called function notation. So this is saying the function of f with respect to x. So in that parentheses, all this is doing is that's representing the input. And so let's just write the whole thing out. So if I want to know where this function is at 1, so I would go ahead and say f of 1, and wherever I see x, I'm going to put in place of it 1. And so I have 5 times 1, which is 5, plus 3, which is 8. So the reader for function notation is basically saying, okay, wherever I put in place of x, I am going to replace it on the other side. It's kind of like this x value here, these parentheses are showing you what's being inputted into the function. And so this is just a mathematical statement saying f of 1 equals, and now I purposely did this because on this side, it kind of looks like the same thing, 5 times 1. But function notation is different. Function notation is just telling the reader, hey, I have a function. That's this line, the original one. And then this line here is saying, hey, in that function, I am replacing x with 1. And I'm trying to find out what the actual value is at 1. And so it's just a different way to display a function of two variables. And very often you'll hear, and if you scour the web, you'll see that f of x is basically the same thing as y. Now, you can think about it like that to help you realize that there is not too much of a difference, which is fine. It's just the way things are noted. So, when you come across some other letters, we can get pretty specific then. So instead of like f of x, g of x, the generic ones, like number 2 here, I have a C, I have an N. So we can actually go like this. C of N equals 12N minus 100. So we're not just restricted here. We can make the functions look like the actual formulas or equations that we have, just to emphasize the topic at hand. And then there's something like this one down here. Now, let me just ignore this arrow here for a second. And this one here, d equals 50t. So we can go d of t equals 50t. And so there, again, that does not mean d times t. We wrote this in function notation, which tells the reader, hey, I have a function d, and I am going to have an input of whatever t is. Now, this is kind of like a distance formula. Distance equals rate times time. So, I mean, that's just kind of what that particular function represents. So, we have lots of different things that go on here. Essentially, functions, equations, they're pretty much the same thing. It's just how it's displayed. And so there's some advantages to one versus the other. So now down here it says write an equation with 2 variables. And so let's just focus right here, number 8 here. We have C of N, so we have some more specific variables, there you go. And so this one, we can go C equals 15N plus 90.
Again, if you need any assistance, just please make sure to email me, text me. I'm here for you, and I hope you have a blessed day.